This is the pre-lab lecture for Lab 4. We're going to look at large signal behavior of BJTs this lab. So first thing to know is if you haven't gotten to it in class, there are 3 models for a BJT. So just like a diode had 2 different models when we were doing hand analysis, open or closed, and the open model was either a wire or a 7/10 of a volt drop, and the closed model or the off model was just a gap. Transistor models are similar. There are 3 different modes that this can operate in. They're called active, saturation, and cutoff. And the active mode, VBE, is 0.7, and then IC is beta IB. In the saturation model, you just have 2 different voltage drops of 200 and 700 millivolts. And there's not necessarily a relationship between IC and IB. In the cutoff model, you can either have 2 reverse bias diodes or you can just have gaps here. Either way, the model shows that there's no current flow from C to B or from C to E, either one. So the way that you choose between these is by assuming a biasing arrangement. So if you assume that VCB is positive, or VBC is negative, either way, and VBE is positive, or more specifically, more than 0.7 volt, then you're in the active mode. If VBC is lower or negative, then you could be in the saturation model. Often we look at VCE here, and if we say VCE is 0.2 or more, then you're in the active mode. If you're less than that, you're in the saturation mode. So it's really, this is driven by VCB and VBE. So if VBE is positive, you're either active or saturated. If VBE is negative, or not quite 0.7, then you're cut off. So VBE drives things, and then VC determines whether you're in active or saturation. So you'll get lots of experience with the different models in class and in this lab. One of the things that I want to emphasize on this lab is the difference between design and analysis. If we're trying to shoot for a given operating point or a given VCE IC in a circuit, then design means that you would assume that VCE and IC are as you wish, and then you compute the resistor values that make that thing work. Contrast that with analysis, which is what I call homework problems, to where you're given a circuit, including the resistor values, and you just compute what it will do. So these are 2 different things, and you have to be careful not to mix results from design and analysis. They're 2 separate circuits. In one, you have assumed or given VCE and IC, and the other one you have assumed or given resistor values. So what it looks like when you're using this for design is you want a given operating point. So you assume that it's that way, and you compute the component values that work for that. Then you pick the nearest available to those that are actually available in either 5% or E24 resistors or on the capacitor chart. Then you flip into analysis mode. Given those components, what operating point do you expect to see? Then and only then can you really answer the question that you want to, which is, well, are those values good enough? We picked things that were near what we wanted. Is that good enough? And you don't really know until you've gone through this extra step of doing an analysis of your circuit given your lab available values. So be very cognizant of when you're in design mode and when you're in analysis mode. So the device, the specific BJT that we're going to be working with is the 2222, often called the 2N2222. And you can get it in 3 different kinds of packages. So there's a metal can package, and the data sheet shows you a picture from the bottom. So this is the underside view of this, and be careful of that because you have to kind of flip it upside down, look at it, and say, oh, okay, it's emitter-based collector going clockwise, and then you have to flip it back around and remember that the emitter is closest to this tab, and it's emitter-based collector. So this is, when you have it right side up, backwards from the symbol that we draw over here. So it's emitter, base, collector going clockwise. So it's emitter, and then base is off on the right, and then collector is on the top if you want to orient it that way. So that is a little bit backwards. Resist the temptation to bend leg 2 across, though, so that it looks right, in quotes. So that it looks right according to your diagram, because there's a great potential to short out leg 1 and 2 or leg 1 and 3 when you do that. The case is also connected to the collector, so shorting against the case would be bad as well. There are also 2 plastic packages, and unfortunately they have different pinouts. So the 2N2222A or the PN2222A has this arrangement. So there's emitter base collector. So if you put the flat spot on the right, it kind of looks like it does in the diagrams. However, the P2N2222A, there's that one little difference here, has a different pinout. So this is collector base emitter as opposed to emitter base collector. So here you have to put the flat spot on the left to make it work the way that you expect to see it. We have all 3 of these in our cabinet in CSI, so be very careful that you understand which one you're using, and any of them will work just fine. But be cognizant of that. That can lead you to hook it up wrong and things don't work normally. So let's look at the data sheet for the 2222 for a minute. So these are the maximum ratings for this. You notice that VCE is 40 volts, VCB is maximum of 75, but VEB, so the emitter base junction, is only 6. So this base emitter kind of drives the train, and it's the most sensitive of them. Also notice that without a external heat sink, this thing can only handle 625 milliwatts. So you want to be real careful that you're not asking it to dissipate too much current or too much power. Above 25 degrees C, so if it's hot out, like in an automotive situation, you actually have to derate it. It can get rid of less heat by 5 milliwatts for each degree. So you have to be careful. If you put an external case on it, a big metal heat sink or something like that, it can about double it, so it can go all the way up to 1.5. Notice that the power dissipation we usually approximate as VCE times IC. So anytime I ask you to approximate power for a BJT, you can use this equation. There's also a VBE term in there, but it's negligible because it's VBE times IB, and IB is 100 times or so less than IC, so you just throw that one away. The other thing to remember is that you can actually ask Circuit Lab to just compute P directly. And I'll say more about that in a minute. So turning to the second page of the data sheet, you notice that beta, or HFE, the forward DC current gain, is all over the map. It varies with IC, and it varies a little bit with VCE, but really it varies with IC. So you want to be sure that if you know about what your operating point is, you use a beta that corresponds to that. So there'll be 3 circuits that you're going to be working with in this experiment. The first one is a fairly classical arrangement. We ground the base, and I'm going to go ahead and tell you use a 10 kiloohm resistor there, and we'll just compute RC and RE in the pre-lab examples. The 15 volts and the negative 15 volts are literally the 15 and minus 15 ports on your protoboard, and then you'll just ground that one. Then you'll put the BJT in there like that with the collector, base, and emitter junctions. Now when we're analyzing it in the pre-lab examples, you'll see that we don't analyze this component. Just like we didn't analyze diodes, we replaced it with something simpler. We analyze this component and we replace it for, let's assume, active. So you put in the active model, and then you'll analyze it using the active model, and then afterwards you'll check it to make sure that that is an appropriate model. The second circuit then uses a single power supply and ground, and then I use 2 base biasing resistors to generate the base voltage, so that biases that base emitter junction appropriately. Now this is too complicated to model, so what we'll do is we'll take this 15 volt supply and these 2 resistors, and we'll disconnect it, compute the Thevenin equivalent of this stuff, and put that in here. This 15 volt supply here and these two resistors get replaced with this 5 volt supply and this 33.3 kiloohm resistor. So these are Thevenin equivalents. They're not actual things that we'll build. Assuming, again, the active model, then we have a circuit that we can analyze. And in the examples, I analyze that for you. The third example is a circuit that uses just a fixed 5 volt supply. This is not a recommended biasing arrangement, but it's just here for an example. So we use a 10 volt supply on the top and then a 5 volt supply on the base. We replace this with an active model, and then we'll analyze this model. And then this particular one in the pre-lab examples fails the check. So this is not an accurate representation. So we tried this model. It didn't work. It fails the checks. So let's try again. So let's try the saturation model. We replace it with this model, and then we analyze it and we check the checks. So there's a separate document that walks you through the analysis of each of these three circuits, giving you all the equations to do that. So for the pre-lab, so let's look at the pre-lab. So what are you going to do? You're going to redesign circuit number 1 with E24 values. You redesign circuit 2 for E24 values. And then circuit 3 already has E24 values, so all you need to do on that is do the analysis step and repredict V and IS based on your values. So once you've gotten all those hand computations to be done, and you can just turn those in hard copy, you don't need to typeset it or anything like that. I want you to go into Circuit Lab and go ahead and simulate the first one. We'll do the other two in lab, but if you do the first one, that'll get you up to speed on how to do the simulation and all that thing. So you're just going to be doing DC analysis for this. And do be sure to actually use the BJT and double click on the BJT and choose the 2N2222 model. Don't use the active source with the battery and the dependent supply or any of that kind of thing. Let it do the hard work. And then in lab, we'll simulate 2 and 3, and then we'll build all 3 of them and compare the hand model to the simulated model to what we see in lab. I will see you in lab.